you for the invitation and this opportunity to speak here. And today I will show you how chirality basically interplays with hydrodynamics and how quantum effects, namely Barry phases and anomalies, have classical hydrodynamic counterparts. And this work will be based on several collaborations I did with Johnson from Chicago now, Logan Ayagam from IIS, and now Paul Wiegman, who is a professor in Chicago. So let me give you a brief motivation. So hydrodynamics is a very universal effective field theory, and it has many applications. I would say that it's one of the most useful theories in physics. For example, it has a revival recently because of applications to heavy ion physics and also condensed matter system. And many examples of application of hydrodynamics include quark gluon plasma, neutron stars, black hole physics, and condensed matter physics. Includes quantum Hall physics from coupled electronic systems or called atoms. And in this talk, I will focus on
not mentioning river flow.
For example, but I guess that's
too simple.
That's more like engineering. So I'm not sure.
But it's separate hydrodynamics.
Or blood flow.
It's like physics interest these days. So of course, there's like big community in mathematics, in engineering that deals with hydrodynamics, but I would say that not many physicists. So usually physicists more like care about quantum effects. At least that's my experience. Yeah, we can also, of course, deal with classical systems like river flows, but what I'm going to tell you it's probably not related to that. So after giving you some physical intuition, I try to be more technical and describe how this whole story interplays with kinetic theory, how you can describe partition functions, and give you some future directions like anomalies of discrete symmetries or anomalies out of equilibrium. So to warm up, I would say that when I started thinking about that, I learned from Russian friends of mine that all you need to know about hydrodynamics is basically in volume 6 of Lifshitz, and there is no parity breaking effects whatsoever. So one may ask the question, is this story well posed? And for many years people thought that parity breaking has nothing to do with hydrodynamics, and there were good reasons for that, related to second law of thermodynamics. But I will try to convince you that if we include anomalies, then parity breaking effects are not only possible, but required by the presence of anomalies. So to start, let me give you some physical intuition. So imagine we have two heavy nuclei that collide in RIG or LHC. So after the collision, there is this blob of matter that forms in the middle, and it's very hot. There is magnetic field created, and in particular there is chiral particles that basically quarks that flow in that blob. And the point is that if we include chiral effects, there should be some chiral separation effect, namely the quarks with two different helicities should flow in in different directions, and this effect is related to quantum anomalies, and there are particular transport coefficients that are completely fixed in terms of underlying quantum anomalies.
So what is quantum mu exactly?
So I will tell you precisely in a moment.
If there are more than 3 equations with unexplained symbols, audience might get
So
lost.
that's sort of a warm-up. I will give you the details in a moment. So yeah, let me start with quantum anomalies. So suppose we have a fermionic field interacting with a gauge field that is massless. So we can construct a Lagrangian, which is basically psi, deep psi, where d is the covariant derivative. And then the partition function for that can be constructed, and formally it leads to some determinant of the operator d. Now we can at the classical level, we can do the Chiral transformation in this form, where beta is some local function of the coordinates. And then it turns out that if we quantize the system, that the symmetry is no longer there, but actually there is some breaking by quantum effects, and this effect is known as a quantum anomaly. And then Fujikawa realized that even though the Lagrangian is invariant under that symmetry, the quantum partition function is not, because the measure explicitly breaks that symmetry. And technically, if we do the transformation, then there is some Jacobian that precisely leads to the anomaly, which in the case of the gauge field being the electromagnetic field is some coefficients that is Curie fields, and then it's F wedge F. So as a result, at the quantum level, the nether current corresponding to that symmetry.
And this C sub A is somehow related to beta.
No,
It's a coefficient.
It's a parameter.
Yeah. So you have to, for example, you can calculate
Well,
it using
there is a beta introduced, so
Don't look at the Feynman.
so from
integral and beta.
from where
You can
something.
do straightforward field theory, and you find that the diagram, which
Yeah, I know, but I mean CA must depends on beta.
no.
So
CA
what
has
kind of a coefficient is it? A number.
built from the charge.
Ah, okay, that is the
Yes.
yeah.
Yeah, so you can basically calculate the triangle diagram.
Okay, it's just constant.
Yeah, it's just constant, and it's calculable for
Must
or a
have the
different
right
theory.
dimension.
Yeah, but
So now, let me show you how to combine that anomaly with hydrodynamics. So, what is hydrodynamics? Basically, hydrodynamics is a theory that is usually defined in terms of gradients. So, we have some conserved quantities, like energy momentum tensor and the current, and we impose the conservation laws, and then expand our energy momentum tensor and the current in the gradients of the fields that we have, namely the temperature, chemical potentials, and velocity. And you see here explicitly that the zero order term.
somewhere there is a pointer.
Yes.
Down there.
So the zeroth order term is known as the perfect fluid,
In what sense it's zero order? It's
zero
an
order
ansatz.
because there is no derivatives of the field. So I told you that you construct this effectively as some expansion around
But
the field.
unless we know what is u mu, we don't know whether it is not an expansion. I mean, if imagine this is a conventional hydrodynamics, then
This is
u is a
conventional.
gradient.
This is
Let me
conventional.
finish. There is something which is called a potential flow. Then the vector velocity is a gradient of a scalar function, and then this is a quadratic function in a gradient. So what means expansion in gradients? This is not an expansion, this is a consecutive relation. You assume that the energy momentum tensor for a system which is described, you first have to find the degrees of freedom, which is in this case a velocity and probably density somewhere, which is the little n. And then these coefficients, epsilon p, capital P depends on this n. And the only expansion I can envisage in this formula is that the pressure is not a function of a u or its gradient. But that is not an expansion, it's an assumption. There are substances for which this equation is invalid.
Yeah, exactly. But I'm not.
So it's not an expansion of anything. I mean, an expansion that there is a universal function t mu nu, which you can expand. What are the coefficients? What is it? On what the t mu nu on the left side depends, so you can expand it.
What is the expansion parameter? In other words?
There's no expansion parameter.
No.
There
must
is-
be.
There is an expansion parameter,
What?
and
Then what
in
it is?
hydrodynamics, the expansion parameter is basically the long wavelength. So
No.
it's
That's wrong.
It's
That's fundamentally wrong statement. Hydrodynamics does not contain a notion of a wavelength. This expression has not, it's an, I mean, in a
Implicitly, it
hydrodynamics,
does.
we're
So-
talking about the hydrodynamics, not about anything like anomalies and anything. Then in the hydrodynamics, there is a specific concept, which is called the consecutive relation, which tells me how the energy momentum tensor in your formulation is expressed in terms of the fundamental fields of the theory. Here, I assume that the fundamental field is a velocity, fluid velocity, and the density, right? And there may be chemical potential for some reason, which is getting complicated because the question is that the chemical potential is a free energy per unit volume, so you start having a difficulty with it. But that's
Excuse me, if I may suggest, perhaps the ratio of the mean free path with respect to the typical wavelength where these...
again wrong. Hydrodynamic exists without the notions of the mean free path. It's a science which describes the matter which might not be built up of atoms.
That's one way.
So this, yeah, but never mind. I mean, this is not an expansion of anything.
but
There is no second.
No, wait.
try to think about it in terms of effective field theory. So you have some underlying microscopic description, and then you want to take somehow the hydrodynamic limit of that. So that's the setup. So in that setup, you are interested in like long distances, because otherwise,
But that is not an expansion, because there is no way how you can expand. The procedure in a kinetic theory of deriving hydrodynamics of microscopic picture is not an expansion. The derivation of a hydrodynamic equations, for example, from a Boltzmann. Now, I'm trying to understand. This is assumption which is called this is an ansatz. Period. Let's go further.
yeah. So I mean, I guess it's more
But
like
in order to talk really about the expansion, one must define the theory,
Yes, the left hand
which
side,
is then depending on some parameter, and then
yes.
the expansion in this parameter will give you this.
And the
Since we have not seen yet the theory
Yeah.
for which this is the first order, this discussion is...
Oh, wait. If this is, no, because if you have an effective theory for T mu nu, you fix degrees of freedom, and the right-hand side can be arbitrary function of degrees of freedom of and their derivatives, which is consistent with any symmetry which you impose, I guess, Lorentz symmetry here. So you always can imagine that there are other terms which contain derivatives. Why not? Of all these parameters which are there. And this is an effective field theory, and then even if you don't have the underlying specific underlying microscopic theory, you can try to propose a set of experiments and fix to fix the coefficients experimentally.
Exactly. So,
But I have another question, a little bit more general. I mean, the chiral anomaly is of course there because pi zero decays into two gammas. So if angular momentum is conserved, the helicity cannot be. Is there any deep experimental reason why we suspect that chiral anomaly play a role in hydrodynamics?
so I think it's nowadays under consideration. So one possible setup is like heavy ion collisions. Another possible setup is, let's say, Weyl semi-metals, for example, or some chiral condensed matter systems.
I mean, long before the Selig path integral formulation of anomaly was discovered, people knew that there is anomaly, and there were a lot of explanations, triangle diagrams, maybe a little less general, but we were convinced that it is correct theory because of experimental evidence, right?
Yeah, that's true. But as I told, there was this, I think, argument by Landau that because of the second law, I will tell in a moment about that. People did not
Landau
expect
book is
that-
about classical physics, and classically, I mean, anomaly is a breaking
Yeah, so
of classical symmetries by quantum
But
effects. So
even without anomalies, you can, in principle, write down terms
yes,
that are parity breaking.
Sure.
And Landau argued that because the second law would be violated, as I will show you, then we shouldn't expect anything like this. But anomaly is sort of like a robust argument that it has to be there. So okay.
So the second law.
So a second law. So okay, but wait a moment. I will tell.
Of thermodynamics.
I will tell the details in a minute. But before that, let me define the setup. So if we agree that this is our hydrodynamic expansion or ansatz, then this is like zero order in the gradients. Then we have some correction that are first order in gradients, and then the zero order is covariant. However, if we go beyond zero order, there is some ambiguity in our definition of the degrees of freedom, and this is known as hydrodynamic frames.
So this is still not complete, since we don't know what tau mu nu and what nu mu is. Therefore, this system is not yet well defined.
Yeah. So epsilon is the energy density. P is pressure.
Yes.
U's are the velocities, and
But clearly, you need some more relations because you only have 5 equations.
Yeah,
and you have
exactly.
Many
but
variables.
In addition, we have to know how P is
Yeah, of
related
course.
to epsilon.
yeah, exactly. So we have to close the system with some additional relation, but I will need that here. So
Because the P is not actually a pressure in
Yeah.
relativistic theory. Because you cannot define the pressure as a force on a unit surface.
so yeah, I agree. So, but I don't need that for my purposes. So I haven't specified that. But so let me tell you about hydrodynamic frames. So we know that velocities, temperature, and chemical potential do not have microscopic definitions out of equilibrium.
Why velocity? Velocity
Velocity
It's not a thermodynamic.
is by definition out of equilibrium. In equilibrium, velocity
We
is
have
zero.
always redefined the field and called this that this is our new velocity. So it's a question.
Velocity is a statistical object here. It
No,
arises from
U is the
gradient of
element of
velocity.
the Tracher tensor. Okay? And now the question, what is T? Which did not occur in the previous slide. And how do you define the temperature? I mean, on the previous slide, we can see there were only epsilon and a pressure, which
Yes.
actually is an epsilon times derivative epsilon with respect
That's-
to the n minus
That's
epsilon.
what I'm telling them. There is some freedom in defining those quantities.
No.
Because there is
I
no.
mean, if there is a freedom, I can define them equal to anything I want. I mean,
Yeah,
But
precisely.
the freedom means that we still need more equations to solve this.
Yeah, but we are trying to expand something.
No,
So
we are not trying
the
to-
capital T has to be defined somehow. And how it is related to the previous slide. I know that we can expand and have freedom, but how is the temperature defined in this object, in this framework?
So for the moment, temperature is some scalar field in the setup.
In addition to epsilon and P.
In addition to epsilon and p.
Okay.
And then there is some freedom in defining that. So we can add some correction to velocity that obeys this equation, because in relativistic theories u mu is equal -1, and the same goes with temperature and chemical potentials. That's why to get rid of that ambiguity, people usually choose some frame, which usually is like Landau frame, which is this condition, which means that the observer is sort of flowing with the energy, and other conventional choice is the so-called Eckhart frame, which means that the observer is flowing with matter.
How does this fix the frame? The u is a variable here, which varies from point to point. Velocity is, I understand, a field,
So
which is defined over the whole space-time.
So basically the point is that you have some expansion, so in gradients, and then because of that freedom, you can sort of have more terms in that expansion. So to fix that expansion, you impose the frame. Because
But what does it mean physically that you fix the frame? What is the physical definition of this frame? I understand the frame of reference, right?
yeah, so it's like positioning your observer with respect to the fluid.
But the equations that you wrote were relativistically invariant.
Only the zeroth order.
No,
If you go to
what you
the
had before, they were relativistically invariant.
Conversion.
yeah,
Well, the form is
This-
invariant.
Yeah,
this
form
part,
conversion.
this part, that's true. But here there is some ambiguity. That's what I'm telling. I'm like,
But in order to show this ambiguity, you must define what is tau mu nu. What is it?
yeah, I will do that in a moment. But I'm just trying to give you some physical intuition that.
So the
The
purpose,
question is
the purpose
that
now
we
is
want
to
to,
find tau mu nu.
the expansion here means that we have a non-dissipative fluid, Euler fluid, which is described by this first part of the equation, epsilon plus capital P plus P times J mu nu. This is the Euler fluid. And the tau mu nu in the Landau book, and this famous book number 6, describe the part of the energy momentum tensor which describe dissipative corrections
Friction.
and friction of the viscosity, because it has to be and therefore, in order to have that concept of viscosity, which is very well defined there, and there where the expansion in a gradient occur in the Landau book, that in order to have that independent of the frame of the reference, that it will also relativistically invariant, has to fulfill a certain additional condition. And in the hydrodynamic, thermodynamic, in relativistic hydrodynamics, there are several suggestions how this condition should lie. One is by the Eckert, one is by the Landau. the other is by the Donder and the others. And there is a complete review of a relativistic hydrodynamics written by Maria Eke and myself, where all the consequences of choosing different types of these conditions are discussed in details and related to the kinetic theory. And one of those conditions is the Landau condition. There's also Van Kampen condition, if you will, and so forth. And they, in some sense, define the temperature. That's the problem.
Yeah, so now we start with these two equations, and then we want to construct the entropy current for that system. So hydrodynamics is a very special effective field theory. Namely, there are some additional constraints, and one of them is the second law of the thermodynamics. So how to do that? We basically add these two equations together, play around with them, and then we arrive at this equation, and then we call this quantity the entropy current of our system.
But there was no S in the previous set of equations. How can you derive this equation from the other
Yeah, so
equations?
you use the first law of thermodynamics, basically. So
You add to this,
Yeah, you add
the whole thing, I mean, because the hydrodynamics is not anything it's a defining a concept. So we have a fields U, we have a fields N, and we have a field S. And we write an assumption how these fields, what are the equations these fields are based. They are not expansion of anything, they are assumed and written.
yeah, so
Right? We know from experience, experiments, etc., how they should look like. And then there is also the additional expression that the entropy must increase. So we try to construct the relativistic equation, and I don't remember whether it looks like this.
yeah, so if you look in like all
But that is probably what you can find in the Landau-Lifshitz book.
Landau-Lifshitz.
That this is the equation which, in a plain language, means that some kind of a relativistic time derivative along the path of a particle, of the fluid particle, not the physical particle, of an entropy increases. And that's this equation. You take a parcel of a fluid, looks on its word line, and look what entropy evolves on that line, and it cannot decrease. So that is the equation, how it is derived. It's additional equation,
So
as good as postulated.
having that, we can ask what happens if we add terms that break parity. So one of possible terms in relativistic fluids is the generalization of vorticity, and this is given here in this form. And in principle, if we add it here, then because of the Levi-Civita symbol, the second law of thermodynamics might be potentially violated. That's why Landau said there is no terms like that in the entropy current. However, this is exactly
My
why.
argument is that it's quadratic in velocity.
Yeah, it's quadratic
Yes,
in
and you
velocity.
can kill a Landau argument. Okay. No.
Yeah, so, but basically, we need a positive definite entropy current. And that's why adding terms like that, in principle, could violate that. And that's also the case.
What does it mean, positive entropy current? It's a field. The second law doesn't say that locally any quantity has to be positive. So what do you mean by the saying that entropy current has to be positive? What means that the vector is
Does
positive?
it mean that S is positive?
It means that the
Vectors
Current
cannot
cannot be positive.
the divergence
cannot be
of-
positive by definition.
of the entropy current.
But what does it mean that the entropy current is positive?
So that the entropy is not generated.
Yeah, but that may happen when the Eugenie may have a different. The entropy is generated in any heat engine, so it cannot be. There is no physical statement that the entropy cannot be generated. I'm now generating as much entropy as you can.
Yeah, that's true. But
So I can generate. So are you saying that I'm clearly not relativistic now, particularly?
I'm just saying that
You
the
are
second
using words which are completely misleading.
But
the second law of thermodynamics has to be satisfied. That's my point, and you can see it in the.
But you said that the entropy current has to be positive. That is nonsense.
But basically, if you calculate the entropy current for the perfect fluid, you see that.
Four-dimensional vector, so what does
So
it mean?
it is positive.
So if you take d mu s mu,
Yeah.
then it's zero. So you see that entropy is not generated in your
The
system.
current, entropy current is conserved. That this is what you
conserved,
mean?
Yeah, that is the different statement.
The entropy current is conserved.
That's said. That's okay.
For the perfect fluid, but if you include dissipation,
yeah, exactly. I would expect that for the perfect fluid it is conserved, and if you include dissipation, the divergence has something to do with
The
dissipation.
dissipation.
Yeah.
yeah, exactly. So that's the first order. So that's exactly given. So this tau mu nu and nu mu is first order. So it's related to dissipation in the system. That's why, in this case, there is no problem. But if you add vorticity to that with some coefficient, then there is potentially a problem.
But that's not the vorticity, because it's a quadratic function of velocity.
It's relativistic generalization of vorticity.
No, I mean, relativistic generalization of vorticity is epsilon mu nu times, I mean, it's a tensor. Dual tensor to the derivative of u. I mean, I can define the relativistic vorticity, which is linear function of u. That was the key point in the Landau discussion, that the dissipative terms in the hydrodynamics, only in the Navier-Stokes hydrodynamics, are first order gradients of velocity.
So
And therefore, our argument was that if you stay within the conceptual framework of hydrodynamics, where dissipation is a function of a first-order derivatives of velocity, because a friction in the physics is related to how two layers of fluid move with respect to each other, and that is a first-order derivative of a velocity, not a quadratic function. And the argument of Landau was that if you stay within the limit, that conceptual framework, you cannot fulfill whatever you wrote. But then you say, okay, I can do it with the quadratic function. But then that don't use the word. You cannot blame Landau for anything. He was not talking about it.
Yeah, so at least now I'm saying that because the magnetic field in coupled to hydrodynamics has similar properties as vorticity, or this generalized vorticity, then similar problem may occur if we calculate the divergence of the entropy current. And now there is.
Wait. B mu was defined before as the scalar product of u and f, right? Is this what you had before?
Yeah, so
Okay, B
is
is the
this
dual.
one.
Yeah, okay. the rest frame of the fluid, this is magnetic.
Yes,
Yeah.
exactly. And now the conservation of energy management tensor, the current is broken, and it's in this form. But again, if we calculate what is the entropy current, now we have enough equations to fix the functions that let's say we put in front of these terms, and then from that we can also fix some transport coefficients that occur in the current, and as you see, they are proportional proportional to the anomaly coefficients, and they're purely given by the chemical potential, energy density, pressure, and charge density.
So, what are really the assumptions and what are the consequences of these assumptions? Because do you postulate the form of the current here?
Yes, so
Of the entropy?
I write some expansion for the.
Let's not talk about the expansion. You define the current in this.
So I define all the currents and energy momentum tensor,
Okay.
and then
There is also the question that somehow we are still missing the relation between temperature, entropy, and intensity, because we have too many functions.
yeah. So I also put that.
There must be a relation between epsilon P, S, and T. Otherwise, you have epsilon P, S, and T, 4 unknown functions. You have to specify.
Yes, I have
Otherwise,
the
it's not an equation.
first law of thermodynamics.
No, the first law has nothing to do with it. First law is a conservation of energy, so it cannot define these things. You have to postulate, you have to make a constitutive relation between entropy and otherwise you cannot proceed with it.
Yeah, that's true. So
You wrote a T, and the question is, what is T and S in this thing? Because previously we had epsilon. P is a spurious quantity, is a derivative of epsilon. But how is that? I mean, we know that the entropy, there is a Maxwell diagram which tells me how the thermodynamic functions are related to each other. And that is also in the Landau-Lifshitz that this thermodynamics can be formulated within the framework of relativistic theory. So all this relation between free energy, chemical Gibbs potential, which is mu, and internal energy, and everything is thoroughly discussed there. So the question is that because of relativity principle, they have to be different than the non-relativistic physics. So you have,
yeah.
so we are missing something here.
What I'm saying, the framework is basically Landau-Lifshitz. I agree that I skipped some details, but you know, it's
This J mu is electric current,
charge current.
charge current. So does that mean that the energy is not conserved? I mean, that there's something,
That's
the energy is not
Because of
conserved.
theory Newton.
that's this current that's coming from charge, from
Yeah,
chiral
but
symmetry.
The dimensions even don't match here.
Chiral symmetry is not charge current. Chiral symmetry, I mean, it's a chirality.
But if this is the
Not-
charge current, then dimensions are not.
No, it's not. If this is a
There is a little
chiral,
j and capital J.
Yes, little j is the, as he said, charge current.
okay,
Yes.
little
Yes,
j,
okay.
that's true.
So this
So
is
the
the current
energy-
that corresponds
So
to the
this
chiral.
first equation looks like corrections to the energy conservation due to Ohm heating.
But there is no coefficient here that will specify.
Resistivity, resistivity is
Yes.
missing.
Yes.
So, yeah, but
That's why
this
it's a
cannot be
dimension.
defined unless you make a specific assumption about the consecutive relation. Because there is
Lucas,
no
you
relativistic consecutive relation. There is no,
So there is some kind of
Ohm law.
Ohm's law, yeah.
the Ohm law is a complicated problem with the relativistic theory.
So can you answer this question about the first equation? What does it really mean physically? That there is heating?
So, anomaly means that there is...
Not talk about anomalies, let's talk about physics. I mean, we have the energy momentum and the current on the right-hand side. It has nothing to do with anomalies. It's a physical statement about the energy of the system and
The first
current.
equation, divergence of
Yeah.
the energy
What
momentum
does it mean
tensor.
physically? You have well-defined concepts: energy momentum tensor, electromagnetic field, and the charge current.
Yeah, so it means that there is some energy pumped to your system, basically.
But then you need some coefficients that would specify the property of the matter that really is related to this physical process. You cannot just take electromagnetic field multiplied by the current, and this does not have the right dimension.
But, okay, I guess probably here there should be the capital J on the right-hand side. But
Capital J?
this is...
That capital J is not the charge current.
No, capital J is the current that corresponds
Yes, entropy.
to the... JS is the
JS,
entropy.
okay.
This current is the one that corresponds to the chiral symmetry breaking, and that's the one that's pumping
The
our...
current cannot correspond to symmetry. The current is something that defines
Something
the
is
motion
flowing.
of the fluid.
Of something that
Of some.
No, here current means a chiral current, axial vector current.
axial vector current.
Okay.
So at the classical level is conserved, but
But we don't know the relation, but there are now 3 J's on the slide. Little j, capital J.
so this is a typo. It should
Okay,
be-
so there are 2 currents.
Okay, so this should be capital J.
Yeah.
Yeah, then there are two currents. The capital J and J with an S.
Yeah.
And how they are related. Because, there is somewhere...
No, they're not.
No, they are not related. The
So-
capital J
So there
is
is
the
an
axial current.
additional
Capital J
equation.
is the axial.
There is an additional equation which about the derivative of a current J mu S. And what is on the right hand side of the derivative of a J mu S? If I calculate the derivative.
So this is entropy times the...
No, there
velocity.
is, the right hand side is equal to the left hand side. So I calculate now the derivative of a capital J mu S.
That was on the previous slide.
The derivative.
Exactly, and I'm saying that if these functions in front of omega and b are of this form,
It's 0.
it's 0. So it's
So the
adiabatic.
anomaly does not contribute to this.
Yeah. Cancels.
So yeah, we have,
It contributes because these coefficients are in D and so. Sorry, that I.
yeah. So that there are like 2 points. One, that we have to redefine the entropy current, and then we want to redefine it such a way that the entropy is not generated, so that our evolution is adiabatic, and d mu s mu or d mu j s.
I assume that
is
the
0.
T is an absolute temperature.
Yes.
Then it's a question with the coefficients T blows up at 0.
Yeah, but Łukasz, not asking about everything at once.
Yeah, so I'm
Not because
running over
T
time.
diverges.
That's true.
So
dT is constant.
one thing is that
Something wrong.
we have some equations that we need to solve, and apart from this, there is some integration constant that at the level of hydrodynamics is not fixed. However, we can fix it using the Kubo formula, and it's related to gravitational anomalies, and it's proportional to t squared. So I don't want to go into details
But
because
what are gravitational anomalies?
so
They require the quantization of the.
yeah. So these are like so you have some Lorentz symmetry and coupled to
So you mean Lorentz
Metric
invariance is violated?
Yeah, if you have chiral fermions and you couple, let's say, curved manifold to that, then Lorentz invariance can be violated. And it seems that there is some transport proportional to t squared that's coming from that. But okay, I don't want to go into technical details now. So one point I want to make is that again, at the level of like intuitive picture, that in usual fluid dynamics, we can define various helicities, and basically they capture the topological properties of the fluid. So they capture how the lines in our fluids are knotted in a sense, and we have this usual helicity. If we have magnetic field, we can also have cross helicity in this form, and we can also define magnetic helicity.
These fields are the velocity fields?
Yes,
That
yes.
And A is probably vector potential.
A is vector potential. So that's part of, say, ongoing work, and it would be interesting to relive this anomaly story to the story of topological fluid dynamics that people have been studying for a long time.
But there is another anomaly which is somehow well-known, conformal anomaly, the non-conservation of the trace or non-zero value of trace of energy momentum tensor in massless theories, which in a classical field theory it has to be zero because it, whatever it can be, but in the quantum theory, as we have this additional scale, it is non-zero. Does it play any role here in this consideration?
Not in this construction, however, of course, there are various anomalies, and after this story emerged, like people started thinking whether there is some transport or some hydrodynamic counterpart also of these anomalies, but it's not studied to the extent that these ones. Also, like there are parity anomalies in odd dimensions, so you know they correspond to like whole physics, for example. That's also like a potential direction. So now let me tell you a bit how one can understand this story from the point of view of kinetic theory. So what is kinetic theory? It's the semi-classical description that deals with the particle distribution function in the phase space, and then given this interpretation, we can integrate f, and this should give the number density, and we can generalize that to calculate the energy momentum tensor if we match the index structure properly and put the relevant relativistic constraint. And then the question is how can we construct the first order gradients in the setup. So if we just integrate this for the equilibrium distribution function, we get the perfect fluid. So now the idea is let's add some.
So now how T is defined?
It's a parameter.
Yeah, it's some.
It's a field
parameter.
Some parameter.
So it also has to.
I think the relativistic definition of temperature is a science in itself, and maybe it's a...
No. It's extremely well defined concept.
Okay.
I mean, there's no such a thing as there's mumbo jumbo about the temperature.
Even the dimensions are not right.
Yeah, I mean,
Again.
okay.
Yeah, so basically the idea is that we add some small correction to the distribution function, and then we integrate over this phase space and see whether it gives the first order hydrodynamics. And indeed, we can use this procedure to construct.
In other words, I mean, for those who may not be experts on relativistic kinetic theory, the Hüttner function, which is a generalization of a Maxwell equilibrium distribution function, which is this coefficient you had written in a fancy way, is extremely well-defined function, and every term in it is specifically defined and can be calculated. There's nothing arbitrary in there. And this has been done in the 20s by the fellow in Singh and the others. It's all extremely well explained in the literature. So just by reading,
You mean F equilibrium?
I understand that this is F equilibrium, which is a function of those parameters, unless it is multiplied by those. I don't.
It's a
Equilibrium
function
is a
of-
function of this single
Yes,
argument.
and that the equilibrium distribution function in the kinetic theory of a free particle so far, this is this energy momentum tensor, it has to, in non-relativistic limit, become a Maxwell function.
Yes.
Otherwise it will be a nonsense. So the generalization of the relativistic Maxwell, generalization of a Maxwell function to the relativistic theory is called Hüttner function. It was derived in the 20s by the fellow named Hüttner. And then every coefficient in it, and also the concept of a temperature are extremely well defined. There's nothing arbitrary.
Okay.
Okay, so does not contradict this.
No, but therefore I'm asking whether this is, why it is written that way.
That way meaning.
No, I mean,
It's not written anyway, it's just a function of this parameter. You say that there is a well-defined function that
It's
No,
okay.
but it doesn't have that
Yeah.
this dependence. That's what I'm saying.
Anyway, let's agree
Except
that
that
you
we
can
need
use that
also-
to derive the
No,
hydrodynamic.
it's not a function of P. No.
And then the question is, can we understand the anomaly in this way? So suppose that we add some small correction to F and try to reproduce the.
which is by an equation for neutrino.
So
What do you mean
like,
by an equation?
we start with the Lagrangian for the massless
Yes, yes, so
chiral
by the
Fermions.
Weyl equation you mean the wave equation for a neutrino, for a massless neutrino.
Massless.
Then why there are no two components in your slide? You don't have two components of this. You only have. Yeah, where are the spinners here?
So there is A and B.
But psi is a two-component object, right?
Yeah.
The right-hand side must also have two components.
Yes.
So they are missing.
So there's something missing here. Usually one writes U of P times the creation annihilation operators, and this U is missing here.
Maybe there is a typo, but so what I'm saying that let's try to use kinetic theory and for Weyl Fermions and try to derive hydrodynamic objects like T mu, J mu, and entropy current. And if we add some linear correction to F, then we can derive T mu and J mu. However, there is a problem in the entropy current because the H function is not linear in F. So, and to derive the right hydro properties by matching, we need some linear correction that we integrate over the phase space. And that's why, so at the end, what happens, we need to modify the density of state structure, and it very much resembles the.
But is this in 3 dimensions or in 1 dimension? Because if it is in 3 dimensions, you need integration over 3 components of momentum.
That's the 1 plus 1 dimensional example.
Ah,
But in principle, you know, it should work in every dimension. So
in 1 dimension it's completely different in 3 dimensions.
So the point is that the story is general to all even dimensions. So
In
you
one,
can,
in one dimension, relativistic hydrodynamics is sick.
I
But
agree.
we are talking now about violent neutrinos.
I agree. I just want to understand like the structure of the tube side. The point is we want to learn something how anomalies interplay with hydrodynamic regime. And you know, you can do that in any even dimensions because anomalies exist there.
Over P, not over the energy, because P varies from -infinity to infinity. So this integral, as far as I can tell, does not represent the solution of Weyl equation.
At least we know why there are no spinors.
Now I understand why there. So psi is 1 dimensional.
Yes,
There-
psi is just.
So what is psi then? What
Greek
relation
letter.
it is to Weyl equation?
Psi is a
What
Greek
is
letter
Weyl
that I
equation
can
in 1
testify.
plus 1? There is no
Inequality.
Weyl equation then, because
So all I'm telling that formally you can define chiral fermions in any even
No,
dimension.
that's true.
And because I want to understand anomalies, I just took this 1 plus 1 dimensional example to learn about the
But
general
free-
properties.
free field of neutrinos is so simple that why do you have to restrict the number of dimensions? Can't you do it in
But in 1 dimension, the anomaly discussion is very transparent. That's at
Exactly.
least.
Exactly. That's the point. So if I can understand
There is a
1 plus 1, I can
physics
easily.
reports by Shuriak, which explains anomaly and it starts from an example 1 plus 1 variable dimensions, and everything is visible basically there, right? So I understand that you can just for training practical purposes start from that example, just to see the general structure, what happens.
So what I want to do is basically I want to calculate the hydrodynamic quantities in the anomalous setup using that kinetic theory approach. The message is I can do that, and this is the result of the calculation. So I have some Gibbs current, and it's of this form. Now, one transparency before I tell you the relation between the topology and that object is that anomalies can be captured by objects called anomaly polynomial, and they're constructed from the so-called characteristic classes, which are topological invariants. So if I formally expand this, I get some functions C1, C2, which are known as Chern classes, and these are examples for the first two, for the F field, and then for the curvature 2 form, I can construct the so-called Pointryagin class, and then the first Pointryagin class is given here. So now if I take the classes and try to describe the generating functions for the anomalies, it's basically in 2D, it's in this form. So there is F squared, and then there is the first Pointryagin class. Now, by inspection, if I compare with this, I see that there is a simple substitution rule. So if I exchange F by the chemical potential, and if I exchange the contracting class by minus T squared, then it seems that the finite temperature transport is very similar to like zero temperature anomaly, which means that we have some finite temperature counterpart of the anomaly polynomial. And then if I generalize to higher dimensions, then as I told you, I need to have some modification in the density of space, which is of this form. This works in all 2n dimensions now, and it can be constructed by matching the kinetic theory to the anomalous hydrodynamics. And here are the first examples. So as you said, like, 2D is very special. It's very easy, and many features can be understood there. So, for example, this form has been known for a long time. It follows from the Cardy formula and the first law of thermodynamics. And you can generalize to higher dimensions, and you see that there is no vorticity in 1 plus 1 dimension. Nevertheless, there is some effect. However, in higher dimensions, there is some terms proportional to the vorticity and to the magnetic field. So this is capturing basically this chiral vortical effect. So the separation of the chiral particles if you have rotating fluid, and this is the so-called chiral magnetic effect. So
what is the meaning of the sentence, Cardy entropy formula plus first law of thermodynamics?
that means that if you are in the Cardy regime, you take the Cardy formula and assume the first law of thermodynamics. You can derive this expression. In higher dimensions, it's not so easy, but you can use these kinetic field techniques. Okay, and now I want to show you that that there is a big connection between that and the Berry phase. So suppose you have some Hamiltonian that depends on a set of parameters. Then if the system is adiabatic, we have some dynamical phase, and we have also some non-dynamical degree of freedom, which is now called Berry phase, and it was
Or geometric phases.
or geometric phases. And yeah, it was noticed in 80s by Berry. And then using that, we can, for example, explain the Karplus-Lattinger velocity. So suppose we have some Fermi liquid, we have some excitations close to the Fermi surface. So we can write down the Lagrangian of this form, where this is the vector potential, and this is some potential in the momentum space. We derive the equations of motion. We see that there is some correction to the usual case, and that's precisely the Karplus-Lattinger contribution to velocity. So omega is a gauge-independent object, and it's known as the Berry curvature. And in this setup, in order to have the Liouville theorem satisfied, we have to basically solve these equations on the equations of motion here, and then we exactly see that once we do that, there is some modification of the density of states that also gives rise to a new phase invariant phase space element, and this is precisely like analogous to what we have.
The Berry phase is a concept so well studied, that kinetic equation by the solid state physicists, that most of what is written, I mean, what is the relation between P in elastral and the K and things like this? We know exactly that the Newton theorem holds for Berry phase systems. You just have to define a phase space properly.
Yes.
So
That's
the-
all I-
this
that's
is
all I'm
all.
saying.
This is. I mean, this is.
Okay, but we have to
Yeah.
Converge.
come to.
We have to wrap up this somehow.
Converge.
I guess somewhere three halves. Okay, but so the message is that this Berry phase can lead to the anomalous non-conservation of the current, and that's I think it's a new development.
Now, but that is known since years. This expression. The last one. This expression has been derived in the various versions by Andy MacDonald, Joshua Zark, Gil Kerr, and myself. It's in the solid state physics. I mean, the children knew it. So it's nothing new.
Yeah,
Sorry.
The connection between anomalous hydrodynamics, I would say.
No, I mean, you okay.
So,
We don't
anyways,
care
that's
so much about it.
just to mention some words that we can use this this anomalous hydrodynamics to let's say study the phase space or phase diagram of chiral fermions. So there are some, let's say, intuitions about phase diagram of QCD. So in our case, it will be like temperature versus chemical potential. And one nice tool to do that is the so-called information geometry. So I don't want to go very deeply into details, but the point is that we can construct the so-called Fisher information matrix, which has all the properties of the metric in the phase space. And then the nice feature of that is that the second order phase transitions correspond to divergences of that metric. So we can, because our transport is non-dissipative, and in principle we can calculate all those free currents, Gibbs currents. Then we can use that as our probability generating functional, and then use that to describe the information geometry metric on that anomalous space. And this can be done, and I'm just saying that there are some critical points for the
Could you
rotating
please
fluids.
sum up this?
Yeah, so the conclusion is that it seems by now that the anomalies are important for hydrodynamics, and there is a very nice story, I think, that has connections with Berry phases. There are like developments in different directions, like different anomalies, let's say, non-relativistic limits on that, and perhaps in future it can give some insight about the non-equilibrium physics. Thank you.
Thank you. Questions?
We already had a lot of questions.
Yeah, during the talk. Okay. Thank you then.